Here, we're asked to find the domain and range of a given function. We know the domain includes all input values except those that make the denominator 0. So, to find the domain, we must set the denominator equal to 0. When you solve the equation, you get x equals 7, meaning the denominator is all numbers except for 7. Next, to determine the range, we must analyze how the graph behaves. Since the denominator x minus 7 is squared, it is always positive, meaning the function is always positive. This makes the range all positive numbers greater than 0. Here, we are asked to find the domain and range based on a graph. Since the domain is all possible x values, we need to first locate the vertical asymptote since we know our function cannot equal these values. Here, you can see there's a vertical asymptote at x equals -1. This makes our domain x when x is not equal to -1. To find range is very similar. We first need to locate the horizontal asymptotes since we're looking for all possible y values. Here, we have a horizontal asymptote at y equals -2, meaning the range is y when y does not equal -2.
Hello everyone, my name is Ida, and I'm going to show you how to find the real vertical, horizontal, and oblique asymptotes of rational equations. The first equation that we have is Rx is equal to 3x plus 5 divided by x minus 6. To find the vertical asymptote, we must set the denominator equal to 0 and solve for x. The denominator for this equation is x minus 6. So we set that equal to 0, and that's 6 to both sides of the equation. Positive 6 plus negative 6 is 0, leaves x behind. Positive 6 plus 0 is equal to positive 6. This leaves x is equal to positive 6 as the vertical asymptote for this equation. The horizontal asymptotes are based on the degrees of the equation. The numerator's degree, or n, is equal to 1. The denominator's degree, or m, is equal to 1 as well. If the numerator's degree and denominator's degree are equal, then the horizontal asymptote will be based on the coefficient ratio of the equation. If the numerator's degree is smaller than the denominator's degree, then the horizontal asymptote will be 0. If the numerator's degree is bigger than the denominator's degree, there is no horizontal asymptote and an oblique asymptote instead. Since the numerator's degree and denominator's degree are equal for this equation, the horizontal asymptote will be based on the coefficient ratio of this equation. The numerator's coefficient is 3, and the denominator's coefficient is 1. 3 divided by 1 is 3, means that for this equation, the horizontal asymptote is y is equal to positive 3. The next equation, Rx, is equal to 8x squared plus 26x minus 7 divided by 4x minus 1. The vertical asymptote can be found by setting the denominator, in this case 4x minus 1 equal to 0, solving for x. First you set 4x minus 1 equal to 0, then you add positive 1, then you add 1 to both sides of the equation. It's easy with 4x is equal to positive 1. Then you divide 4 on both sides of the equation. It's easy with x is equal to 1/4 for the vertical asymptote for this equation. Horizontal asymptote will be based on the degrees of this equation. The numerator's degree, positive 2. The denominator's degree is positive 1. Since the numerator's degree is greater than the denominator's degree for this equation, there is no horizontal asymptote for this equation. Since there is no horizontal asymptote, there is going to be an oblique asymptote for this equation instead. The oblique asymptote is found by dividing the polynomials of the equation. It can be found by dividing 8x squared plus 26x minus 7 by 4x minus 1. 4x goes into 8x squared 2x times. 4x times 2x is 8x squared, and negative 1 times 2x is negative 2x. When you subtract 8x squared minus 2x from 8x squared plus 26x, we're left with 28x. The negative makes negative 2x squared positive, and then you add 26 to get 28. Then you drag negative 7 down and add it to 28x. 4x goes into 28x 7 times, so we put plus 7 up here, and multiply 4x by positive 7, 28x. Negative 1 times positive 7 is negative 7. Subtracting 28x minus 7 by 28x. Subtracting 28x minus 7 from 28x minus 7 will leave with 0. This means that for this equation, the oblique asymptote will be y is equal to 2x plus 7. I hope that this video helped you and hope that you have a great day.
Okay, we're going to quickly go over how to graph functions using transformations. The first thing you want to know are basic pairing functions. There's a lot of them, but you only need to know like a few. So the most common one you need to know is our quadratic function. It's going to be fx equals x squared, and it's going to have that standard parabola smooth shape. The next one we see most often is fx equals x, which is our standard linear line. There's going to be fx with the absolute value x, which is going to be that v-shaped graph. There's our reciprocal function, where it's fx equals 1 over x, which has that opposing L-looking shape. Yeah, that's going to be used for our fractions. And we obviously know sine and cosine functions, which is going to be fx equals sine or fx equals cosine, with sine going through the y-intercept of 0 and cosine going through any number that's not 0. The next thing you want to know are types of transformations. There's plenty, but these are the ones we really need to know. Our horizontal shift is going to be f parentheses x plus or minus h. When it is plus, like when we're adding h, it's going to be, our graph is going to move to the left h units. When we're subtracting h, we're going to move our graph to the right h units. The next one to know is our vertical shift, which is going to be fx plus or minus k. When you're adding k, your graph is going to move up by k units. When you're subtracting k, your graph is going to move down k units. For reflections, if it's negative f times x, it's going to be a negative reflection across the x-axis, and if it's f times negative x, it's going to reflect across the y-axis. For our vertical stretches and compressions, it's going to be a times f of x, which is going to be the absolute value. If the absolute value is bigger than 1, it's going to stretch vertically. If the absolute value is bigger than 0 and smaller than 1, it's going to compress vertically. Kind of similar for horizontal stretches and compressions, it's going to be f times ax. If a is bigger than 1, our graph is going to compress horizontally. If it is bigger than 0 but smaller than 1, our graph is going to stretch horizontally. We know that our graph is going to move left 2 units. As far as graphing it, we can go back to our knowledge on parent functions, and we see that with the graph they give us of y equals x to the power 4, that is most closely related to fx equals x squared, which is our quadratic function. Now, if you remember what our quadratic function looks like, it's just our basic parabola, and because it's just standard and nothing else going on with it, we know it's going to be a simple parabola on the y-axis. But if we relate it to the function that MMO gives us, because we already know it's a horizontal shift, and it's plus 2, as mentioned before, we're going to move our graph 2 units to the left. So this is what it should look like. And there you go, now you know the graph with transformations. Okay, now we're going to walk through how to graph using our 8-step process. It's very simple if you just follow the steps. Now with our example problem right here, the first thing we're going to do in step 1 of the 8-step process, we're going to find the domain of the rational function. So to find the domain, we're going to set the denominator to 0, which would give us x equals 1 and x equals negative 2. Now because this graph is going to go on for infinity, we have to factor in infinity into our intervals. So because we already had that x is going to be equal to negative 2 and 1, we're going to put negative infinity and negative 2 and 1, and then 1 and positive infinity. So now we have a total of 3 intervals. Step 2 is to write our function in lowest terms, but lucky for us, our function is already in lowest terms. Yay! But if it wasn't, you have to factor. Okay, step 3, find the intercepts. The x-intercepts are going to be the zeros that are in the numerator and also a part of the domain. But because you can see our numerator is x, we're just going to say that our intercept would be our origin point, 0, 0. Okay, step 4 is to find the vertical asymptotes. To find the vertical asymptotes, you just set the denominator to 0, which we already did. So our asymptotes would be the same as our domain. It would be 1 and negative 2. So you're going to make a dashed line through negative 2 and 1. So step 5 is to determine any horizontal or oblique asymptotes. And there's neither horizontal asymptotes or oblique asymptotes because the degree of the numerator is less than the degree of the denominator, because there's 1 up here and there's 2 down here. Step 6 is a little tricky, but for step 6, you just want to test each one of our intervals and see if they would be below or above the x-axis. I'll show the work I did for reference, but I'm just going to walk through one of them. We can walk through negative infinity and negative 2. So to test that one, you just find literally any point, or you can pick any number between negative infinity and negative 2. I'm going to choose the next nearest one, negative 3. And you basically just want to take the factors from the denominator and set them to the number you chose, so negative 3. So basically it would be x minus 1 equals negative 3, and then x plus 2 equals negative 3. Now x minus 1 equals negative 3 actually results in negative 4, which is a negative number. And x plus 2 equals negative 3 equals negative 1, which is another negative number. So from that, we know that because it's negative, it's going to be below the x-axis. And as you can see, I'm going to put my work, but you just do that to each one of your intervals. Step 7 goes hand in hand with step 6. You're just going to be analyzing the behavior, like where the lines are going to go near the asymptotes. This is where the parent functions come in handy. We know that 2 out of the 3 intervals are going to look like this, like our reciprocal parent function, because we know that the function they give us is a radian fraction. So 2 out of the 3 of them are going to have this weird L looking thing. And step 8 is to actually draw the graph, so I'm going to walk us through that. So we're going to mark our asymptotes, which are going to be negative 2 and 1 to show the division and our line breaks. And then we're just basically going to graph each interval. Like I went through in step 6, we know that this one is going to be below the x-axis and it's negative. And because it's infinity, we're really just going to be focusing on the negative 2. To draw, you're basically just going to put it near your asymptote of negative 2 and just put it like this, going opposite and away. Opposite and away infinitively, like infinitely. The next best one to graph would be the one closest to our asymptote of 1, which would be this one because it's positive, and because of step 6, we know that this one is going to be above the x-axis. To graph this one, you just basically do what you did for the other one. You go 1 unit past your asymptote, and then you just go up and extend infinitively in the little shape that we would know if you know your parent functions. Insert this one right here. Lastly, we graph this one, and from step 6, we know this one is going to be on our origin, and it's going to be going opposite ends infinity. And here's our graph using the 8 steps. Yay!
Alright, the next topic that we're going to be doing is going to be holes versus asymptotes. And the equation that we're going to be doing is x plus 3 over x plus 3 times x plus 6. So the first thing that we're going to do is asymptotes. And the first asymptote we're going to do is going to be vertical asymptotes. And the rule for vertical asymptotes is you're going to take your denominator and go to 0. So we're going to look at our equation and we're going to x out x plus x bottom. And then we're going to take x plus 6 and equal that to 0. We're going to minus 6 on both sides. And then x is going to equal 6. And that will be our vertical asymptote. Right, next for our horizontal asymptote, we're going to have 3 rules. Usually for horizontal asymptotes, we use something called big fractions, which could be generalized as fx equals ax plus dot 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 over bx plus dot dot dot. Okay, so considering this, here are the rules. If n is less than m, then a horizontal asymptote would be 0. If n equals m, then y will equal a over b. And then if n is greater than n, then we're going to have no horizontal asymptote. So considering this, we're going to look at our problem, and our n is going to be 0 because we don't have a numerator on top, and then our m is going to be 1. So 0 is less than 1, so that means our horizontal asymptote will be 0. Will be 0. All right, now we're going to find the holes, and in order to find the holes, we're going to take the removed pair and then equal that to 0. It's almost the same as broken asymptotes. So we're going to take our removed pair on our equation, and that's going to be x plus 3. We're going to equal that to 0, so minus 3 on both sides. We're going to have x equals -3. And then -3 is going to be a hole. And then that's all. Let's go off to the next problem. All right, for this problem, the first thing that we're going to do is simplify. All right, so what we're going to get if we simplify them all, we're going to get x plus 4 times x minus 2 over negative x minus 2, minus 2, and then x minus 4. So we're going to cross out x minus 2 on the top and bottom, and then we're going to find our vertical asymptote. So we're going to take x minus 4 and equal that to 0. 4 plus 4. X is going to equal 4. And then to find our horizontal asymptote, we're going to look, and we see that we have a 2 and a 2 here. So that means they are equal. So we're going to do 4 over negative 4, which is going to equal negative 1. So then now to find our hole, we're going to take our removed, which was x minus 2, and then equal that to 0, add 2, x equals 2. And that will be it. And this is all for holes and asymptotes.
For our last topic, we'll be doing inequalities with rationals. So this is our first problem. I like to color code my problems with greater than as pink and less than as blue. So the zeros of the numerator are x-intercepts, zeros of the denominator are asymptotes. We're going to set those equal to 0. And this is what we get. We're going to make our number line, and we're going to put all our little zeros in there and our asymptotes. And then we're going to put in numbers in between. We have 8, 1, and -1, and 6. We're going to plug these back into the problem. And so -6 gets us a negative number, -1 gets us a positive number, 1 gives us a negative, and 8 gives us a positive. Since we're looking for pink numbers, we're going to X out our blue numbers and then write in our intervals. Since it's greater than, then we're going to make sure to include our zeros in there and put brackets. And then this one's a graph, so I like to, again, color code them. And everything that's positive is pink, everything that's negative is blue. Since this is a blue equation, aka less than, we're going to look for our blue on the graph. Since the blue starts at -infinity, we're going to include that all the way to the asymptote at -5, then at the 0, 4, all the way to the asymptote at 0. So everything's going to be in parentheses since there's no line underneath our less than sign, and this is going to be what you get. Okay, and now we're going to solve another one of these. It's already a pink question because it's a greater than sign. And the zeros of the numerator, we know how to solve those. Zeros of the denominator, aka asymptotes. We're going to make our number line, put all our numbers on there, put numbers in between those numbers, and we're going to plug them into our equation. And we see that -6 is positive, 0 is negative, 4.5 is positive, and so is 6, giving us -infinity with the parentheses, comma, -4, bracket in union with bracket 4, and positive infinity with the parentheses.